Welcome to the ant universe. This will be the first in a bunch of these small videos that I can now make easily and upload on YouTube by some magic pixies. That will be designed to supplement some of the more difficult concepts in the class. I hope they turn out to be useful. If they're not useful, let me know. So, here we have the ant universe without anything in it. I'm going to put some ants in it in a little while. And we're going to do our best to make the ants explode their little tiny heads when they have to think about something. So, let's imagine our ant universe looks like this. And I, for the most part, will remain off camera because you don't need the hideous experience. So, here's our ant universe. We can imagine it as a flat rubber sheet, very, very flat. And the ants are essentially massless ants, so their mass doesn't produce curvature on our rubber sheet. So that's our rubber sheet if we look at it top down. If we look at an edge view of our two-dimensional rubber sheet, hey, it's a straight line. I don't know what that crap is, but I might need it later. I don't want to break the universe either. So there's a repair, not very good. So we have two ants, and trust me, I draw like crap, doesn't matter, but I have no idea what this is. So there we go. If I could copy and paste from this, I would, but I can't. So we have two ants with enormously long feelers and very short legs, and I don't know where the other 6 legs are. But there's our two ants. We have ant A and ant A prime. And over here, we have two other places in the universe, B and B prime. And we spent a long time training our ants so they'll walk at a constant velocity. So ant A is going to walk in that line to point B, and ant A prime is going to walk in that line to point B prime. We've trained our ants to walk at a constant velocity. We have provided our ants with synchronized stopwatches, which they'll wear on their feelers, okay? Stopwatch. Fine. They synchronize their clocks here. Clocks at this position, position 1, and then they want to compare what their clocks read when they both arrive. I almost gave it away when I said simultaneous at B or B prime. And so the ants start walking at exactly the same time and at exactly the same velocity. And since they're covering exactly the same distance, it's pretty obvious that A and A prime, I'm not going to redraw the ants, show up at B and B prime at the same time. And so if you ask the ants, how you doing, how was your journey through the universe, did you notice anything peculiar? They look at each other, they look at their clocks, and say, no, dude, everything's fine, no problem. All right, simple case. Now let's explode their little ant heads conceptually by introducing curvature along one path, but not the other. So in this case, we're going to drop a very large mass that ant A has to walk through, or on, rather. It's in the path between A and B, but there's nothing in the path between A prime and B prime. Now here's the key to this. Ants are two-dimensional creatures. This is a two-dimensional surface. At any given time, whether the surface is flat or curved, it's still a surface. And so if we look at the edge-on view for A to B, it's obviously got a big piece of mass in it. But the ants cannot perceive this dimension. That's the third dimension. Just like you and I can't perceive the dimension in which space is actually curved in, so let's not worry about it. They have no idea. This ant has no idea that, what curved space actually means. And so we're going to then run the same experiment. They start at exactly the same time out here where space is nice and flat for both ants. And this ant, A prime, walks over to B prime exactly the same way as I don't know what sex this ant is. The ant has no idea why we've asked it to do the same thing again, but we have. And we just told them, well, we're doing a tricky experiment this time. And so B prime, when ant goes from A prime to B prime and stops there, there's a certain time, T prime, that he notes. Right? When space was flat, T prime and T were the same between the two ants. But now, by the time when this ant walks this way, and then down this way without knowing it and back up, that way, because that part of space doesn't exist anymore, you can't go on that trajectory, there's no space there, it's been curved by the mass here. Obviously, this ant has walked a longer path length, and since they're at a constant velocity, then it takes longer for ant A to get to B because of the presence of this curvature. But the manifestation of that is that when ant A gets to point B and measures their time, oops, their time does not equal T prime, the time of the other ant. As far as this ant goes, time has run slower. That's what mass does, curvature does. It will make time apparently run slower in the frame of reference of this ant, even though they've just gone from A to B and A prime to B prime. And then you give a final exam to the ants, and ask why their times are different. Both little ant heads conceptually explode because they have no clue what happened, because this ant has no way of knowing that they're walking through curved space. That's the effect of gravity. And so time runs differently for these ants depending upon their frame of reference. So space-time, curvature, and time are all intertwined. Now, the degree to which time runs slower is a function of the degree in which space is curved, which is a function of mass. So if we make this mass even more mass, then the degree of curvature is, wow, went off the video frame. That's bad. Where's the ant go? It's not coming back. It's gone. So the degree of curvature is more, so time runs proportionally slower. So time runs slower in strong gravitational fields. And this effect has been measured. Gravity in an airplane is slightly less than gravity at the surface of the Earth because you're farther away from the center of the Earth. So if you tow an atomic clock in an airplane, you can show that clock runs very slightly slower than an atomic clock sitting on the surface of the Earth. Again, the key to this is to understand that the universe is a surface, just like this thing is a surface, and that mass produces curvature. That curvature occurs in a dimension that we don't have a perception of, other than the fact that it exerts a gravitational force, but it still is a surface. And in essence, the presence of mass, each one of these is a little mass, creates more and more surface area in the universe. So that's what the curvature of space-time is. Mass, curved space-time. That's what Einstein identified as gravity. Newton assumes that space is flat everywhere. Since Mercury is in orbit about the sun, it's actually orbiting in curved space. And so each elliptical orbit precesses and is different from the elliptical orbit to come. That's not explainable in Newton's flat space. It's a consequence of Mercury orbiting in curved space because it's sufficiently close to the sun. So, that ought to be enough confusion for now.